In this section, we'll talk about the sum and difference identities for the sine and cosine. In earlier sections, we were able to determine the value of trigonometric functions for some of what we call the common angles. For example, we know that the sine of 30 degrees is equal to 1/2. We also know that the cosine of 5 pi over 4 is equal to -√2/2. But what if the angle given is not one of our common angles? Then what do we do? For example, consider 75 degrees, which is not a common angle. What is the sine of 75 degrees? Of course, with a calculator, we can determine that the sine of 75 degrees is equal to 0.9659258263, which makes sense because of the location of 75 degrees on a circle. The problem with this answer is that it's an approximation. To get an exact answer, we need something else. What that something else is to rewrite the given angle in terms of two common angles. So, in this example, we could write the sine of 75 degrees as the sine of the quantity 30 degrees plus 45 degrees, or even the sine of 135 degrees minus 60 degrees. But then what do these equal? It's a common misconception to think that the sine of 75 degrees is equal to the sine of 30 degrees plus the sine of 45 degrees. Remember that sine by itself holds no meaning, so distributing it isn't something that means anything. Secondly, if we were to find out what the sine of 30 degrees is and the sine of 45 degrees, 1/2 plus the square root of 2/2, and find out the decimal approximation to this, we would get 1.207106781, which is not equal to what we said above was 0.96 approximately. So, what else can we do? Sum and difference identities for cosine and sine will allow us to find the cosine and sine of some of the angles that we're not familiar with. The sum identity for cosine says that the cosine of the sum of two angles is equal to the cosine of the first angle times the cosine of the second angle minus the sine of the first angle times the sine of the second angle. For the difference identity for cosine, it's the same exact thing, only in the middle, instead of a minus, we now have a plus. For sine, the sum identity for sine says that the sine of the sum of two angles is equal to the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. For the difference identity for sine, it's exactly the same thing, only instead of the plus that we saw in the first identity, we now have a minus. Now, you might be wondering, where the heck did these things come from? In this video, we're not going to prove the identities, but if you're interested in seeing that proof, you might check out this YouTube link down below. So we're going to try an example. We're going to take a look at finding the exact value of the sine of 75 degrees. Now, there are several ways to write 75 degrees. I could write it as a sum. I could also write it as a difference. I'm going to write it as a sum. I'm going to say that the sine of 75 degrees is equal to the sine of 30 degrees plus 45 degrees. Now, I have to identify the identity that I should use, and so I'm going to pick this one here. That's the sine of two angles, the sum of two angles. So I'm going to use this identity. And so let's see what I've got here. I'm going to say that this is equal to the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. Now, these are all angle measures that I do have memorized, so I don't need my calculator. The sine of 30 degrees is 1/2 times the cosine of 45 degrees, which is the square root of 2 over 2, plus the cosine of 30 degrees, which is the square root of 3 over 2, times the sine of 45 degrees, which is the square root of 2 over 2. Now I'm going to multiply. So the first term becomes the square root of 2 over 4, plus the second term becomes the square root of 6 over 4. And that's a perfectly good answer. However, since they do have a common denominator, I might want to write that as the square root of 2 plus the square root of 6 all over that common denominator of 4. Now let's look at another example, this time with the cosine. We are being asked to find the exact value of the cosine of 75 degrees. I'm going to pick the same angle measures that I picked before, the 30 and 45 degrees, but now I'm going to pick the cosine sum identity. So that's up here at the top. Okay, so I'm going to be carefully making sure that I plug in those numbers. So the cosine of the sum of 30 degrees plus 45 degrees is going to equal the cosine of the first angle times the cosine of the second angle minus the sine of the first angle times the sine of the second angle. And again, I have these memorized. Let's see, what's the cosine of 30 degrees? That is root 3 over 2 times the cosine of 45 degrees, which is the square root of 2 over 2, minus the sine of 30 degrees, which is 1/2, times the sine of 45 degrees, which is root 2 over 2. Okay, and so when I multiply this, I can already see that I'm going to have a common denominator, so let's go ahead and just write those all together. This is going to equal the square root of 6 minus the square root of 2 all over 4. Now, you might be wondering, where would I use something like this? Well, music is made up of vibrations that create pressure on our eardrums. Musical tones can be modeled by sinusoidal graphs. When more than one tone is played, the resulting pressure is equal to the sum of the individual pressures. So we're talking about the sum of two sinusoidal functions. And we'll take a look at an example of something like this a little bit later. Now let's take a look at an example where we're asked to find the exact value of the cosine of pi over 12 radians. The previous examples have asked us to find the sine and cosine of degree measures. Let's see how radian measures might be different. The only thing that makes these different, we're still going to use the same identities, is that our angle measure may be more difficult to find a sum or a difference of. In this case, pi over 12, we need to rewrite pi over 12 as the sum or difference of two angles. Now, in this case, it's probably going to be the difference, and that's because unless I want to use negative radian measures, finding a sum is going to be challenging. Now, one of the things that often causes students problems is figuring out what two angles subtract to pi over 12. And what I want to show you here is how you might go through that process. I usually just pick a radian measure. So let's say 12 pi over 12. And if I subtract from that 11 pi over 12, that will get me 1 pi over 12, won't it? The problem with that choice is that 11 pi over 12 does not reduce into anything that I have memorized for the sine or the cosine. So that's not going to work. Let me keep going. How about 10 pi over 12? If I take 10 pi over 12 and I subtract from it 9 pi over 12, that will work, won't it? And that's because if I reduce this, I get 5 pi over 6 minus 3 pi over 4. Both of those measures are angle measures that I do have their sine and cosine memorized, so that could work. But let's keep going and see if there's any other choices. Let's pick that 9 pi over 12, and if I subtracted 8 pi over 12 from it, I would get 3 pi over 4 minus 2 pi over 3. That could also work. So I've got two choices now. Let's keep going. 8 pi over 12. I could subtract from that 7 pi over 12. But 7 pi over 12 doesn't reduce into anything that I can use, so just like with the 11 pi over 12, I'm not going to choose this one. All right, so let's go to 6 pi over 12. I could subtract from that 5 pi over 12. That 5 pi over 12 does not reduce, and so I'm not going to use it. How about 4 pi over 12? I could subtract from that 3 pi over 12. Does that reduce? I think it does. That's going to get me pi over 3 minus pi over 4. I like that. Can I go any further? Yes. Let's try 3 pi over 12 minus 2 pi over 12. And I think that that reduces. That'll reduce to pi over 4 minus pi over 6. So that works. And one more. 2 pi over 12 minus 1 pi over 12. Well, the problem with that is that 1 pi over 12 is the angle measure that I'm trying to actually solve for, so we know that's not going to work. So we have 4 choices listed here. You can use any of them. I just want to point out that there's more than one way to do these problems. I generally like to pick the option that has the smaller numbers. So what I'm going to do is probably pick this pi over 4 and this pi over 6. I like those because I have an easier time memorizing the sine and cosine of angles that fall in the first quadrant. Okay, so here's what I've got. I'm going to say that the cosine of pi over 12 is equal to the cosine of the quantity pi over 4 minus pi over 6. And that's going to equal, I'm going to use the difference for cosine identity down at the bottom that says that this will equal the cosine of the first angle, so the cosine of pi over 4, times the cosine of the second angle, so the cosine of pi over 6, plus the sine of the first angle, pi over 4, and the sine of the second angle, which was pi over 6. Now, because I have this memorized, I don't have to use a calculator. The cosine of pi over 4 is square root of 2 over 2. The cosine of pi over 6 is square root of 3 over 2. Plus the sine of pi over 4, square root of 2 over 2, times the sine of pi over 6, which is 1/2. Looks like I'm going to have a common denominator of 4. So in my numerator, I'm going to go ahead and just write square root of 6 plus the square root of 2. And I'm done. I have found an exact solution or exact simplification for the cosine of pi over 12. Now, that answer may look familiar to you. A couple of slides back, we saw that the sine of 75 degrees equaled the same thing. So why is that? Well, you may recall from a past lesson that we said if two acute angles, an acute angle is an angle that's less than 90 degrees or less than pi over 2, if those two angles are complementary, meaning they add to 90 degrees, then their cofunctions are equal. What the heck does that mean? Well, it turns out that pi over 12, if I multiply this by 180 degrees over pi, turns into 15 degrees. All right? So if I consider the cosine of 15 degrees, what that identity for cofunctions tells me is that the cosine of 15 degrees is equal to the sine of 90 degrees minus that 15 degree angle. Well, 90 degrees minus 15 degrees is 75 degrees. So the reason why those two answers are the same is because the cosine of pi over 12, and the sine of 75 degrees are cofunctions. And we know that cofunctions are equal, so therefore we would expect their exact values to also be equal. Let's try another example. Find the exact value of the sine of 11 pi over 12. 11 pi over 12 is not an angle measure that we have memorized, so we're going to use the sum or the difference identities for sine in order to find that exact value. Now, we can rewrite 11 pi over 12 as a sum or even as a difference. I'm going to choose a sum identity for sine, and I'm going to say that the sine of 11 pi over 12 is equal to the sine of 2 pi over 12 plus 9 pi over 12. Now that's just what came into my head. There are other options, and I would encourage you to try those other options and just confirm that you get the same answer as me. I'm going to rewrite 2 pi over 12 as pi over 6 and 9 pi over 12 as 3 pi over 4. So using the sum identity for sine, I'm going to say that this is equal to the sine of the first angle, which is pi over 6, the cosine of the second angle, which is 3 pi over 4, plus the cosine of the first angle, pi over 6, times the sine of the second angle, 3 pi over 4. Sine of pi over 6 is 1/2. The cosine of 3 pi over 4 is negative square root of 2 over 2. The cosine of pi over 6 is square root of 3 over 2. And the sine of 3 pi over 4 is the square root of 2 over 2. If you really challenge yourself to calculate those angle measures that we've learned about, to do those by memory and not to use a calculator, you're going to get really strong at finding sine and cosines of those common angles. So let's go ahead and put this final answer over that common denominator of 4. I'm going to get negative square root of 2 plus the square root of 6 all over 4. Now that's a perfectly good answer. A lot of times you'll see in books or answer keys that they don't like to lead off with a negative because it could be confused with subtraction. So because addition is commutative, I could rewrite this as the square root of 6 minus the square root of 2 all over 4. Let's try another example. In this example, there's going to be 4 parts, and I'm putting the first 2 parts on this first slide, and then we'll hit the second ones in just a minute. We're given that the sine of an angle alpha is equal to 3/5, where alpha is between pi over 2 and pi. Now that's important information because that tells us that alpha is in quadrant 2, right? Alpha is in quadrant 2. And that the sine of beta, a different angle, is equal to negative square root of 5 over 5, where beta is between 3 pi over 2 and 2 pi. So beta is in quadrant 4. All right, and we're being asked to find the cosine of alpha and the cosine of beta. Let's start with the cosine of alpha. Now, here's what we know. We know that sine squared of an angle, we'll call it alpha, plus cosine squared of alpha is equal to 1. So I should be able to find out what cosine of alpha is by simply substituting in the sine of alpha, which is 3/5, into the location in the Pythagorean identity and squaring it. Notice that alpha is not 3/5. I'm not substituting in for alpha. I'm substituting in for the sine of alpha, and then I'm squaring it. So 3/5 squared plus the cosine squared of alpha is equal to 1. So I'm going to get that cosine squared alpha is equal to 1 minus 3 over 5 squared. Well, 3 over 5 squared is just 3 times 3, which is 9, and 5 times 5, which is 25. Still don't need a calculator. What is 1 minus 9 over 25? I'm going to think of 1 as 25 over 25. And 25 minus 9 is 16. Keep that common denominator. And now I'm going to square root each side to get that this is equal to, it would be plus or minus, right? That's what happens when you square root, 4/5. Now, is it the plus or is it the minus? Well, we are in quadrant 2, aren't we? We're in quadrant 2. Alpha is in quadrant 2. And so in quadrant 2, what sign is the cosine? That would be negative. So cosine of alpha is equal to negative 4/5. Okay, let's go on to part B. Going to use the Pythagorean identity again. Of course, in this case, sine squared beta plus cosine squared beta is equal to 1. I'm going to substitute in this whole sine of beta for the sine of beta, and then I'm going to square it. I'm going to square it. All right, so what is negative square root of 5 over 5 times itself? That's going to get me, well, negative times a negative is a positive, and I'm going to get 5 over 25, which I think I could reduce, couldn't I? I could reduce that to 1/5. 1/5. All right, plus the cosine squared beta equals 1. So cosine squared of beta is equal to 1 minus 1/5. So in this case, I'm going to rewrite 1 as 5 over 5. So 5 over 5 minus 1 over 5 is 4/5, isn't it? And I'm going to square root each side. And I'm going to also rationalize the denominator. This is going to give me square root of 4 is 2, and the square root of 5 is the square root of 5. So I mean, I could write this as 2 over square root of 5, but I'm going to rationalize it because most books are written that way. This is going to be 2 times the square root of 5 all over 5. And is it a positive or is it a negative? Right? This came out positive or negative because we square root it. We're in quadrant 4, and in quadrant 4, the cosine is positive. So there are my two answers. Now let's look at the second part of this question that asks us in part C to determine the cosine of the quantity alpha plus beta, and in part D, the sine of the quantity alpha plus beta. In order to do this, we need a couple of things. We might want to refresh our memories on the identities, and then I think we're going to need the answers that we got for part A and B, namely that the cosine of alpha is equal to negative 4/5, and that the cosine of beta is equal to 2 times the square root of 5 over 5. So, part C. Find the cosine of alpha plus beta. Down below, we see that the cosine of alpha plus beta is equal to the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. All right, so I think I have all those things. Let me just write this out. Cosine of alpha plus beta then is going to equal the cosine of alpha, and the cosine of alpha we found on part A was equal to negative 4/5. Again, that's not what alpha equals, that's what the cosine of alpha equals. So that goes into this whole position. We're going to multiply that by the cosine of beta. The cosine of beta we also found on the last slide, but that was part B. We found that to be 2 times the square root of 5 over 5. That's the second piece. Now we're going to subtract, and we're going to subtract the sine of alpha. The sine of alpha was given to us in the original problem as 3/5, and we're going to multiply that by the sine of beta, which was also given to us in the original problem as negative square root of 5 over 5. So now I'm going to multiply. In the first term, in the numerator, I have negative 4 times 2 times the square root of 5. So I can multiply the negative 4 and the 2 to get negative 8 times the square root of 5 all over 5 times 5, which is 25. All right, the second term, I have minus 3/5 times negative square root of 5 over 5. So that's going to give me plus those double negatives, and I'm going to have 3 times the square root of 5 over 5 times 5, which is 25. Now, a nice thing has happened on this one. We can actually add because we have the common denominators, but not only that, these numerator terms both are square root of 5. We have negative 8 square root of 5. We have 3 square root of 5. So altogether, we have negative 8 plus 3 square root of 5. Negative 8 plus 3 is negative 5 times the square root of 5 over 25. And that's a really nice answer. However, I do see that these numbers on the outside, the 5 goes into itself once, the 5 goes into 25 5 times. I can't do anything with that number underneath the radical because it is sort of trapped under there, but I can do something with the numbers that are on the outside. So this final reduced sum becomes negative square root of 5 over 5. All right, let's do the same exact thing, but this time for the sine. So what is the sine of alpha plus beta equal to? So I'm going to pick this first identity that says the sine of the quantity alpha plus beta is equal to, let's see, the first one is the sine, let me get my pointer out here, the sine of alpha, and the sine of alpha was given to us as 3 over 5 times the cosine of beta. What's the cosine of beta? Cosine of beta we determined was 2 times the square root of 5 over 5. I'm going to add to that the cosine of alpha, which I determined was negative 4 over 5. And I'm going to multiply that by the sine of beta. The sine of beta was given to us as negative square root of 5 over 5. Okay, so now I will multiply all of that out. This is going to give me, in the first term, I see I've got a 3 and a 2, and I can multiply those to get 6 times the square root of 5 all over 25, plus I've got a negative 4 times a negative square root of 5. That's going to get me positive 4 times the square root of 5 all over 25. So same thing that happened before, I've got that common denominator, and in the numerator I have 6 square root of 5s and I have 4 square root of 5s. So all together I have 10 square root of 5s all over 25. And 10 and 25, the numbers on the outside, reduce. 5 goes into 10 twice, and it goes into 25 5 times. So my final answer in reduced form is going to be 2 times the square root of 5 all over 5.